geometry or uh, example, for example. Let me. Let consider this example, a one-dimensional model or ordinary differential equation minus u double prime x equals a function called f for x between 0 and 1 with the boundary condition u0 equals 1 equals 0. We can define, we have the definitions of v prime as the differentiation of v with respect to x or dx dv with dx. The first one called the Newton's notations of differentiation or derivative. The second one called the Leibniz symbol. And f is a given continuous function. By integrating the equation minus u double prime equals f twice, it is easy to see that this problem has a unique solution u. But we recall the boundary value problem D can be viewed as a modeling. In particular, the following situation is in continuum mechanics. The next example in this case called an elastic bar. Consider an elastic bar fixed at both ends, subject to tangential load of intensity Fx, and let sigma, the small sigma x, and ux be the traction and the tangential displacement of x, respectively, under the load or the force of F, and with the assumption of small displacements and linearly elastic material. Let me in order to model this type of elastic bar with the horizontal force or load can be described in this differential equation. Sigma equals E u prime by Hooke's law in the elastic mechanics, or minus sigma prime is equals F, which refer to equilibrium equation in that type of field of mechanics. And with u0 equals u1 equals 0 as a boundary condition in this case. Another example called an elastic cord. Rather than an elastic bar, we have an elastic cord which fixed between at the ends between 2 points with F. You know, F here is vertically applied to this cord. We assume that a small displacement here, so uh, we can have another type of equation to model this system of equation, this system of elastic core. We can also take a look at the heat conduction. Let U be the temperature and Q the heat flow in the heat conducting bar. We assume that we have a bar that can conduct heat through itself. And based on the Fourier laws of heat conduction and conservation of energy, we can model this process based on this system of differential equation minus Q equals K U prime and minus Q prime equals F with the boundary condition here. And here we want to take a look at this type of examples differently from another perspective. We want to find a same minimization problem or same variation problem in mathematics that have the same or equivalent solution to these differential equations. And what we can infer from this paragraph, we shall now show that the solution U of the boundary value problem or differential equation D is the solution of a minimization problem M and a variational problem D. We have a differential equation D and a minimization problem N and a variational problem V that all have the same solution. And we want to formulate the problems, minimization problem N and variation problem V. We want to introduce this notation. The inner product of V and W equals the integral from 0 to 1 Vx Wx dx, where V and W are real valued, piecewise, continuous, and bounded functions. Let's talk about the linear space in this case. V as a set of V, which V is a continuous function on this interval from 0 to 1. V prime for the derivatives of V with respect to X is piecewise, continuous, and bounded on its domain, as you can see, 0 to 1. And V0 equals V1 equals 0 as the boundary condition. And let me introduce a linear functional f from V from this space to the R given by Fv equals a half of 1 second of the inner product of V prime minus F V here is the definition of inner product, as you can see this this formula which I highlighted here. And this function, based on this function, we want to define the problems M as a minimization and V as a variational problem as following. M, the problem M tells us and is subject to finding a U from the above space or linear space of function such that the FAU, F of U became less than or equals to the F of V. The definition of F is in previous line, which I highlight, which it is highlighted here. And in a variational case, we want to find U belong to the space V such that U prime V prime equals F V, and both of these two problems have the same solution and as the differential equation B. So we want to talk about more about the notations here. Let us notice that in the context of the problems A and B above, the quantity F represent or refer to the total potential energy associated with D displacements, and V equals in V, and the term half of V prime as the inner product of V prime and V prime represents the internal elastic energy, and the inner product of F and V, the heat, the load, potential. So we want to associate with it differential equation to a potential function which represents the potential energy, and the differential equation which describe the transferring of the energy from one case to another case. Further, the variational problems V corresponds to the principles of virtual work, in this case, the work and energy. Let us now first show the solution U of E is also solution of V. To see this, we multiply the equation minus U double prime equals F by an arbitrary function V from the linear space, the big V, and a so-called test function V. We integrate over the interval 0 to 1, which gives minus U double prime V equals F V in this case, because V multiplied the sides of an equation, both sides of this equation to the same function. And we want to show that there is the same solution exists for both variational and differential equation V and V. Let us integrate the left-hand side of this equation by integration by parts technique. Taking the integration, you know, this refers to integration as we defined at the first, which I highlighted now, and by taking the integration by part and using the fact that v at 0 and at 1 of both equals to 0, we get minus u double prime v the right at the left hand side of the above equation by taking the integration by part. U prime we have here the u double prime v dx u v dx, and by taking the v and u double prime dx as the w, we can get u prime 1 v1 plus u prime 0 v0 plus u prime v prime equals the u prime v prime, and because v0 and v1 equals 0, so the first two terms of this equation is vanishing, and the remaining term is u prime and v prime. So the left hand side of this equation is u prime and v prime, and we can conclude that u prime and v prime equals fv, which is the we can see u prime is a solution of v because here we have v and u double prime equals f, and here we get the same solution for variational. In the next step, I want to show you the problems v and w have the same solution. V refers to the variationals and M refers to the minimization problem that we have defined in the second chapter. In this here, you know, by proving this fact, we can prove the fact that the V, M, and D has the unique, has the same solution, for example, but let's we want to show that we show that the problems have the same solution. Suppose the first type we use solution is a solution to V. So by taking the V from the space V and set the W as the difference between V and U, and by taking W to the right side and V to the left side, we get, let me here. We can say that U prime, the inner product of U prime and W prime minus F W as 0, and the inner product of the same variable of W, the same vector W prime with itself is actually always bigger than 0. This fact shows that the U is a solution of M, or minimization problems. But why? Because of these definitions of U here. M finally such that the FAU less than or equals find the U than FAV. So we have found such a case. So we have shown that the U is a solution of M. Then we have for any V in the biggest, in the big V, and for an arbitrarily real number epsilon, FAU became less than or equals FU plus epsilon V. So U plus epsilon V is also belong to V, to the linear space V. So we can define a differentiable function G as a function of epsilon by fixing the U and V and taking epsilon as the single variable, and using the expansion of F, we can get this using the definition of F and this expansion meaning equals 1 second U prime F plus epsilon U prime V prime plus epsilon 2 divided by 2 V prime minus F U minus epsilon F V. This function of epsilon has a minimum at the 0 by taking a look at this definition. When the epsilon became 0, these values became, then it takes its minimum. So the derivation, I will share with you after this class. So don't panic. Of course, I will share on our WhatsApp groups. Okay. The fact is that this function has the minimum when the epsilon gets its 0, and in this case, the G prime of a differentiable function at its minimum is actually equals to 0. So the G prime 0 equals U prime minus F V. So we have seen that the U is the solution of V as a variational problem. And here we have shown that there is an equivalence between the problems V, D, and M. And in the next step, we want to talk about the uniqueness of the solution of a variational problem. So we we will take a look at that. Let us also show that a solution to B is uniquely determined. Suppose that then that U1 and U2, in order to show the uniqueness, we just uh, uh, assume that we have two different solutions of V called U1 and U2. So based on the solution of V and based on the definition of V, we will have a U prime 1, V prime equals the, the inner product of U prime 1 and the V prime equals the inner product of F and V. And of course, the same thing happening for U2 and V, U prime 2. V prime, the inner product of these two functions, or two vector in this case equals the inner product of F and V. By subtracting these two functions and using the definition of inner product in this case, and by choosing V as a differential, the difference between U1 and U2, because U1 and U2 belong to V and big V is a linear space. In this case, their difference is also belong to the V because V is a linear space, and we can get these equations by minusing, by subtracting these equations, these two equations from each other. The right side of the both equation, right sides of the both equation are the same, so the difference became the 0, and the left side is remain only from 0 to 1 U prime 1 minus U prime 2 power to kx as a 0. And what we can say about the U1 and the U2 from these integral equations we obtained here is that U prime 1x minus U prime 2x is the differentiation of U1 minus U2 prime x equals 0, because the power 2 here shows us that the function U1 minus U2 or V must be equals to 0 in all points in this interval. So from this inference we can get confident that U1 and U2 are the same, and the variational problem had a unique solution. Let me talk with this paragraph, which is about the uniqueness of U1 and U2, the sameness of U1 and U2. It follows that U1 minus U2x is constant on 0, 1, which together, because its derivatives are 0, with the boundary condition U1 equals U2 as 0, which gives that U1 equals U2 for all the points or x's in this interval, and the uniqueness is simply or consequently follows. So we want to conclude about the concept we have discussed here. The concept is that there is a solution. If we have a solution to D as a U is also solution to the M and V, and M and V in this case is equivalent, and we can show the conclusion or in short like this. Symbolically, B, V, U, the solution of B result is a solution of V, and the solution of V is also a solution of M, and vice versa. Any question about these three different problems here? Here, you know, what we have shown here is that the solution of D is the solution of V, and we didn't show that the solution of V is also a solution of D, because instead of solving D, we want to solve V or M, because there are some benefits when we want to solve a variational or enumeration problem compared to the differential equation. So let us finally also indicate how to see that if U is a solution of V, then U is also satisfies V. So we want to assume that U is an element of linear space V. Let notice the difference between the this V as a class of variational problems, and this V. You know, this is in italic form, and this is in the simple form, and these two are different. The first refers to a variational problem, and this refers to a linear space of functions we have defined. And when we have assumed that U is a solution of V variational problem, so from 0 to 1 U prime V prime dx, the inner product of U prime and V prime, minus the integration of Fv, the inner product of F with V, equals 0 for all V in the linear space V. And we want to show that V is also a solution of U is the solution of D. If we now assume in addition that U double prime, the second derivatives of U exist and is continuous, then we can integrate the first term by parts to get the fact that to get the fact to get the results we want to prove, and by using the fact that the boundary conditions V0, V1 are equals, and the chain vanishes at the 0 or the chain 0, by taking the integration by part, we can get these values minus 0 to 1 u double prime plus f v dx equals 0. We assume that u double prime plus f is continuous in this case, and because this integral is satisfied for every v in linear space v for every v. So that satisfies for v as one, v as another v. We can conclude that u double prime plus f must be equivalent to 0 these intervals, and this is the same as the minus u double prime equals f, which is our differential equation, and every u that satisfies this differential equation is a solution of v. And at the first, we have assumed that the u is a solution of v. So here we have shown that there is a equivalence or sameness between these three problems, M, V, and B, and it's up to us to choose the best problems to solve based on its simplicity. So let me so we have seen that if u is the solution of v as a variational and in addition satisfies regularity assumption, which says u double prime is continuous, then u is the solution of v. It is now possible to show that if u is a solution of v, then u in fact satisfies the desired regularity assumption, and thus we have the v, the solution of v results in a solution of v. And finally, it shows that the three problems B, V, and N are equivalent. And any question in this case? Also, there are sub-problems 1.1, 1.2, which shows us about some examples. We can use in the definitions of V and J in this case. Here we are ready to talk about the principles of FEM or finite element problem in this case. We want the FEM for a model problem with a piecewise linear function. So we shall now construct a finite dimensional subspace V H of the space V defined above, consisting of piecewise linear functions to this end. Let we take partition of the intervals 0 to 1 as x0 less than x1 and x1 less than x2, and this the same hold until xn and xn plus 1 be a partition of the interval 0 to 1. So we divide the interval 0, 1 into the subintervals I index j or ij as the intervals xj minus 1 and xj with the length hj, the difference xj minus xj minus 1, and j is from 1 to n plus 1, and h as the maximum of hj as the norm of this partition. The quantity h is then a measure of how fine the partition h is. We did that h became smaller and smaller. We can see that our partition is bigger, and we have divided the intervals into the small subintervals. We now let VH be a set of function V such that V is a linear on its subintervals ij. V is continuous on 0 to 1, and with the boundary condition V at 0 equals V1 equals 0. So VH is a set of functions such that V is a linear and continuous. So V is a piecewise continuous, and this V prime is piecewise continuous with the same interval. Here, this figure 1.3 shows us an example of V in space of functions VH. So you know, VH is a subspace of V. It's very easy to verify that. As parameters to describe a function V in VH, V may choose the values eta, the Greek letter here, eta G equals V at xj at the node points xj, j from 0 to n plus 1. And we want to introduce a basis function psi in VH, psi j in VH, j from 1 to n, defined for 1 if I equals j, otherwise 0 if I different for j. So here is an example of psi j. We can see this type of function, and we want to introduce our solution to the differential equation as the linear combinations of psi, sum of the different psi, and here is the basic idea of the finite element method. A function v in VH can have the representations v. Every function as this function as v in this figure can be represented by a linear combination of some triangular shape psi as this Vx equals j from 1 to n, eta j, eta I from 1 to n, eta I psi I x x in 0 to 1. So in this, psi at the maximum value of psi is 1, so the parameters neta I equals v at the xi. In the other words, each v h in h can be written in the unique way as a linear combination of basis function psi. In particular, it follows that the VH is a linear space of dimension n with the basis psi I from 1 to n. So the finite element method for the boundary value problem B can now be formulated as follows. Find UH in VH such that f UH can became less than or equals to f of v. F of u became less than the f of v with respect to all v in our space VH. This is a kind of MH minimization problems in this case. So we can also, in the same way, for M and V, we see that MH is equivalent to the finite dimensional variation problems VH. We can find UH in VH such that UH, U prime H, V prime equals FV for all V in this equation. So the finite element method for V can be formulated as a VH or equivalent VMH. The problem VH is usually referred to as the Galerkin's method, and MH referred to Ritz's method. It is easily observed, we can easily observe that if UH belongs to VH, satisfied the previous equation. In particular, we can get the one-pointer equation as the result because this is the same sides equals to each other. So if this equation holds, we can take the linear combinations of elements of psi. We see that the UH is equals to y from n to n, PCI psi I x, and PCI is equals UH at the xi, which we can write this as the 1.3 as the 1.4, the same one. So in this case, 1.4 is a linear system of equations with n equations in m unknown, QC1 to QCn. If we write this in matrix form, we can say that A QC equals B, and A is M multiple n product M matrix with the elements Aij psi prime A psi prime J, and let me remain the remains of this discussion to the next meeting, inshallah, in the Sunday time, because I should go to the I have some problems. I should go to the my and my time is finished. So in this course, in this lecture, we have some discussion about the basic elements of finite dimensional method. So uh, in the next meeting, we will continue that. So let me we will discuss this type of approach towards the ordinary differential equation. It is not very time consuming. We can conclude or reach the conclusion of this approach and finish that in the next meeting, because the main idea of finite element method is to partial differential equation, but here we just only take a look at the application of that approach towards the ordinary differential equation. If you have any questions, go ahead. Otherwise, we will say goodbye. I will share this file now in our WhatsApp group. From page 18, we have page 20. 20 from page 14 to page 20. The other page refers to elementary discussion and introductions of this method. So you need to study these 6 pages, page 14 to page 20, and be ready for the next meeting, inshallah, in the Sunday evening. And we have agreed on the time for the midterm. What? When when we can take the midterm? We agreed on 12 June. You know, our midterm and our final exam date. Can you tell me the midterm and final date? Final exam. We agreed on uh, June 12th for midterm. Am I right? Is that true? Based on the best of my knowledge. من فکر کنم جلسات قبل هماهنگ کردیم برای 12 جوان به عنوان میانترم، درسته خانم طالب؟
بله بله
ادامه دارید؟
بله بله صداتون داریم.
آره.
لا يقول علي لا يقول علي يوم الصناعة امتحان.
برای میانترم بگید آماده باشن. پایان ترم هم تاریخش مشخصه؟
بله
الان میدونید چه روزیه، بگید که ما برنامه ریزی بکنیم.
الان امتحان خرداده
دومه؟
دوم خرداده.
ساعتش هم مشخصه؟
نه من نمیدونم، من میدونم دوم خرداده.
حالا ساعتش مشخصه. خب اینا رو مد نظر داشته باشید. انشالله مطالعه کنید تا من در خدمتتون هستم. اگر کسی سوال داره if any students have questions you can ask me and let me this
فقط موضوع امروز برام بفرستین رو واتساپ برو.
چی؟ حالا الان برای واتساپ به اشتراک میذارم.
دستتون درد.
خواهش میکنم. سلام. Any questions, dear students? I apologize for some inconvenience.
هفته دیگه یک شنبه تعطیله؟
ایران آره، ولی ما میتونیم درس ادامه بدیم. اونجا که تعطیل نیست. عراق تعطیله؟
نه اونجا تعطیل نیست.
و ما چون یه هفته کم نتونستیم ممکنه که ادامه بدیم تا به یه جایی برسونیم، چون دیگه حالا ما یکی دو جلسه بیشتر وقت نداریم. واقعا یه روش رو تموم کنیم و حالا یه جایی برسیم
انشاءالله.
Any question, dear students?